Hey, welcome back to your favorite Fundamentals of College Math class. Going to take a look at the normal distribution and also the 68, 95, 99.7 rule, and we'll go from there. There's our objectives for today. All right, the normal distribution. So it's also referred to as the bell curve or the Gaussian distribution. So it's bell-shaped and it's symmetric about a vertical line through the center. Now your mean, median, and mode are all at the center of the distribution. So for example, this first one here, if you're looking at, let's say you're creating a histogram of 100 men you sampled and their heights, right? And you created those histogram here, it looked like that. If you, let's say we took a larger sample size, so let's say we increased that to 1,000 and then drew that one. It looked like that. Let's say we increased it again and to maybe 10,000, right? And then imagine for a minute that we drew that frequency polygon, right? Where we draw, um, we put a dot at the middle of each of those lines for the frequencies, and then we connected those dots and do that very well. But what you get, and then if we were to smooth that out, we get the bell curve, we get the normal distribution, right? So as you increase your sample size, it looks more and more like the classic bell curve, where your mean, your average, or your median, and your mode of that set of data is all right. That number's all right there in the middle. Okay. Now these are all normal curves, but the standard deviations are all different. And if you notice, like look at the one in green there. This one's standard deviation is very small. So like let's say the scores on the exam, the average is 80%, right? So the 80 is the mean. It's also the median and the mode for your set of data. And let's say your standard deviation is only like 5%. That would be the green one. Real small standard deviation. All the data is real clumped in together. For the blue one, maybe your mean's still 80%, but your standard deviation might be 10% this time. That's the blue one. And then finally, the one in purple there, mean is 80%, but your standard deviation, maybe it's, I don't know, 20%. Okay. So as the standard deviation increases, the distribution becomes more spread out, but it's still bell-shaped. Okay. Now, the 68, 95, 99.7 rule says for our set of data, 68% of the data is within one standard deviation above and one below. Okay, so for example, let's say we had uh, a mean of 80% and our standard deviation was 5%. Where to draw this? Okay, so here's our 80%, the mean, the median, the mode. One standard deviation above, so 80 plus 5 would be 85%. So if somebody scored one standard deviation above the mean, they'd score 85%. If somebody scored two standard deviations above the mean, so they'd go up another 5%, they'd get 90%. If somebody scored three standard deviations above the mean, they'd go up another 5, so 95%. One standard deviation below, so 80 minus 5, 75%. 75 minus 5, 70%. And finally, 70 minus 5, 65%. So this rule says 68% of these students scored between 75% and 85%, one standard deviation below and one standard deviation above. And then 95% of the students scored from 2 standard deviations below to 2 standard deviations above. So between 70 and 90%, 95% of the class scored between 70% and 90%. And finally, let me do another color here. 99.7%, almost 100%, but 99.7% of the class scored between 65% and 95%. So 3 standard deviations below and 3 standard deviations above. Okay. Let's do a problem here. We got male adult heights in North America approximately normally distributed. The mean of 70 inches. Let's go ahead and draw this. So they're normally distributed. Your mean is 70 inches. Okay, that's the mean. So 5'10". And male adult heights in North America have a standard deviation of 4 inches. So let's go up. So if we're 1 standard deviation above, 70 plus 4 would be 74 inches. If we're 2 standard deviations above, we'd be a height of 78 inches. In other words, 6 foot 6 inches. If we're 3 standard deviations above, 78 plus 4 would be at 82 inches. Now let's go 1 standard deviation below, so 70 minus 4, 66 inches. 66 minus 4, 62 inches. And finally 62 minus 4, 58 inches. Okay. Now let's do the problem, right? Because we know this is, we're just trying to get a picture of this. Find the height that's 2 standard deviations above the mean. Well, that's 1 standard deviation above the mean. That's the second one. So I got to go up 4 and up 4 again. So 78 inches. So 70 inches is the mean plus 2 standard deviations. So plus 2 times 4, so we got 78 inches. Again, it's nice to draw that thing, right? We're 2 standard deviations above the mean. So 6 foot 6 inches is 2 standard deviations above the mean. All right, use the distribution of male adult heights in the figure to find the percentage of men in North America with heights between 66 and 74. So let's look at this. 66, so here's 1 standard deviation below, right? Remember, this is the mean right here. And then 74 is 1 standard deviation above. So we know 68% of males in North America are between 66 and 74 inches. So 5'6" and 6'2". Right? Let's do a different one. What if I was to ask you percent that are between about 58 inches and 70 inches. So 4'10" to 5'10". Okay, so what you want to do is you want to use your 68, 95, 99.7 rule again. So we know 68% are between there and there. 95% between there and there, and finally 99.7% are between 58 and 82, so 99.7. Now we're trying to go from 58 to 70, right? 58 to 70. So I'm looking, I'm like, well, this is 3 standard deviations below, right? 1, 2, 3. It's 3 standard deviations below the mean and up to the mean, right? We've got the mean here, 3 standard deviations below. So from here to here, that's what I'm trying to figure out, right? And I know from here to there is 99.7. So I just got to cut that in half. It's half of 99.7%, or 49.85%. Right? Let's do some more here. We've got scores on the graduate record examination, normally distributed with a mean of 578 and standard deviation of 78. So 578 plus 78, we got 656, plus another 78 would be 734, plus another 78, 812. Now let's go down 1, down 2, down 3. 578 minus 78, 500. 500 minus 78, 422. 422 minus 78, 344. And again, remember, 68% of the data, so 68% of those taking the GRE score between 500 and 656. One standard deviation below, one standard deviation above. 95% of these students score between 422 and 734. Nearly everybody, not quite though, but not quite 100%, but 99.7% of all students score between 344 and 812. Now let's answer the question. How many score between 500 and 734? So I'm looking at this and I'm like, well, 500's right here, right? It's one standard deviation below. But then I'm going up here to 734, which is two standard deviations above. So what I'm going to do is I'm going to take the one standard deviation below and I'm going to say, well, it's half of 68%. So 68% divided by 2, I've got 34% for that area. All right, because that's from 500 to 578. Now let's do this part. So from 578 to 734. So there's two standard deviations. I know that the entire two standard deviations below to two standard deviations above, I know that's 95%, but I only want the half of that, right? I only want the one in orange right there. I only want from 578 to 734. So half of 95%. So we got, what's that, 47.5%. So overall, I just got to take the, the whole thing would be the 34% plus the 47.5%, and I'm left with 81.5%. So 81.5% score between 500 and 734 using my 68, 95, 99.7 rule. All right, Z-score. So this is a Z-score is just telling you how many standard deviations above or below the mean you are. So for example, with our male heights, we said the mean was 70 inches and it had a standard deviation of 4, if I remember right. If you were to put this as a Z-score, this is a Z-score of 0. That's 70 right there. This is a Z-score of 1. This is a Z-score of 2, 2 standard deviations above. This is a Z-score of 3. So an 82, since there's 3 standard deviations above, is a Z-score of 3. This is a Z-score of -1, Z-score of -2, Z-score of -3. So again, the Z-score is how many standard deviations above or below, depending on the sign above or below the mean it is. And it is the data item minus the mean all over the standard deviation. All right, so this is the data item. That's obviously the mean, and that's our standard deviation. Okay, so that's a z-score. So we can use that for this question here. The mean height of newborn infants is 7 pounds. You see the 7 right there in the middle. And then it goes up by 0.8 for every standard deviation. So 7 plus 7.8 is 7.8. 7.8 plus 0.8, 8.6, and so on, right? So there's our z-scores right there. That's a z-score of 0, a 7.1 is a z-score of 1, and so on. So find the z-score for a mean of 9. I'm sorry, for a score, for a weight of, for a baby that is 9 pounds. So I'm trying to do two things at once here. And you can see it, you're like, okay, this score of 9 is going to be right there. It's between 8.6 and 9.4, right? That's a z-score of 9. I'm sorry, that's a weight of 9 pounds. So I know it's, if 7.8 is 1 standard deviation above, 8.6 is 2 standard deviations above, and 9.4 is 3 standard deviations above, 9 is right smack in the middle of 8.6 and 9.4. So I know my z-score is going to be 2.5, but I'm going to go ahead and do the math. This will be a very valuable formula for you. What's the z-score for a baby that weighs, a newborn that weighs 9 pounds? What's the z-score? I say, well, what's the data item? 9 pounds. Minus, what's the mean? The mean weight was 7, right? Mean was 7. The standard deviation was 0.8. And then I just punch this in. 2 divided by the 0.8, and you get your z-score of 2.5. So this is saying a baby that weighs 9 pounds is 2.5, that's a big baby, right? Has 2.5 standard deviations above the mean, right? Because the mean baby weighs 7 pounds. And this is a 9-pound baby, right? 2.5 standard deviations above the mean. All right, IQ tests. They're normally distributed with a mean of 100. So you've got a mean of 100 and a standard deviation of 16. So let's go up 16, 116. Let's go up 16, 132. Let's go up 16, 148. Let's go down 16, we got 84. Down 16, we got 68. Down 16, we got 52. Now that's a z-score of 0, that's a z-score of 1 standard deviation above the mean, z-score of 2, z-score of 3, z-score of -1, z-score of -2, z-score of -3. So what's the IQ corresponding to z-score of -1.5? So this time they're giving you the z-score. The z-score is -1.5. So they're saying you're scoring right here. 1.5 standard deviations below the mean. Boom, right there. Right? So what's your score? Well, you probably figured it out. It's right smack dab 1.5 between -1 and -2, right? Right between 68 and 84. Well, halfway between them would be 76. That's what we should end up when we do the math. But let's go ahead and do the math. Z-score x minus x bar over standard deviation. This time they give us the z-score, -1.5. We're 1.5 standard deviations below the mean. I do not know what the data is. I don't know what the test score is, or the IQ score, but I know the mean is 100. I know the standard deviation is 16. So now we just got to do the math. So we do the math. multiply both sides by 16, this side by 16. Negative 24, add 100, add 100, and it looks like there's our 76. Negative 24 plus 100. So yeah, that's 76 is our score, right? That's 1.5 standard deviations below the mean. All right, percentiles. Percentiles. So it says if n% of the items in a distribution are less than a particular data item, we say that the data item is in the nth percentile of the distribution. For example, let's go back to adult male heights. We know that the mean in adult male heights in North America is 70 inches. If you're 5'10", you know half of the data, right? All 50%, because it's below the 3 standard deviations. It includes this little tail down here, right? You're in the 50th percentile. If your height if you are 5'10", 70 inches, and you are the 50th percentile, right? Now, if we go up, let's go up to 1 standard deviation to 74 inches. Now we know 68% of the data is here and here, so this part's 34% right there, right? So if we add in 50 plus 34, if you're 6'2", 50 plus 34, you're in the 84th percentile, right? You're pretty tall. 84th percentile. So that's what percentile is talking about. So how much of the data is below, right? That 84% of adult males are below 6'2". Okay. Now the quartiles, that's just you can divide the data into quartiles, 4 equal parts. This is the 25% of the data here, 25% of data, 25% of data, 25% of data, right? That's your quartiles. Quartiles. In fact, when I give you your scores on the exams, I give you the minimum score. I give you the first quartile. I give you that score right there. That's the first quartile. I give you the minimum score. I give you the median, which is the second quartile. Remember, the mean, median, and the mode is all the same for the normal distribution. I give you the third quartile, meaning 75% of the students scored at that score or below. And then I give the max as well. Right? So the third quartile is the 75th percentile. All right, 75% of the data is all below there. All right, using the Z-score and a table, we can find the percentage of data items that are less than any data item in a normal distribution. And we talked about the mean, median, mode, right in the middle. 50% of the data is all below there. Right? All right, poles and margins of error. So a little commentary on this. So statisticians have shown that the standard deviation of a normal distribution of samples is approximately 1/2 root n times 100%. And so, where n is the sample size. So with the 68, 95, 99.7 rule, approximately 95% of the samples have a population within 2 standard deviations of the true population percentage. So if you take 2 times 1/2 root n times 100%, you get this margin of error. And you can be 95% confident that your true, whatever is coming out of your data, your true percentage is within that margin of error, okay? So that's our margin of error is 1/root n plus or minus 1/root n times 100%. Okay, that's our margin of error. It's like with voting, right? Like maybe they took a sample of, I don't know, maybe back in the Trump election, right, when everybody was off with their samples. Um, Maybe they polled, I don't know, 5,000 people. And they said, well, it looks like when we polled 5,000 people, it looks like, I don't know, we'll say 45% of the population are going to vote for Trump. But you've got this margin of error, right? We obviously did not poll everybody in the United States. We just polled 5,000 people. We think it's a pretty good poll. We randomly selected the people, um, and supposedly 45% are going to vote for Trump. Well, there's a margin of error here. So you plug it in, 1 over square root of 5,000 times 100%. So I punch in 1 over square root of 5,000, and I get 0.01414, blah, blah, blah. Anyways, it keeps going. And then times 100%. So plus minus, so that'll move it over 1.4. So they're like, well, 45% are going to vote for Trump, but plus or minus that. So it might be as low as 45 minus 1.4, so 43.6. This is 45% plus minus this margin of error 1.4%. So 45 minus 1.4 is 43.6%. So somewhere between 43.6 and then if you go 45 plus 1.4 and you get 46.4, it looks like it's going to be somewhere in here is the actual percent that are going to vote for Trump, back in 2016, whatever, right? They had this margin of error, and most of the polls actually the margin of error, from my understanding, was actually correct, even though they predicted the election incorrectly. Very few actually polled it and predicted it correctly, with all the electoral votes and everything. Um, as part of that, they were within the margin of error on that. All right, let's do an example here. This time we got a random sample of 1172 children ages 6 through 14. Here's our sample size, 1172. And they say 17% of children reported that getting bossed around is a bad thing about being a kid. So what's the margin of error? The margin of error, let's do that. Plus or minus 1 over root n times 100%. So we got plus or minus 1 over the square root of 1172. These are going to times it by 100. We got plus or minus 0.02921, blah, 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 times 100%. So we got plus or minus 2.9%. We'll round that, 2.921%. Okay, there's that part. Write a statement about the percentage of children who feel that getting bossed around is a bad thing about being a kid. So what we can say here is, um, we know 17% reported it from our sample, right? 17%. But we have this margin of error. It might not actually be 17%. We only polled 1,172 kids. We didn't poll everybody in the entire country. We don't know what the actual percentage is. We just know we have a margin of error. So if you go 17 minus 2.9, it's 14.1%. 17 plus 2.9, 19.9%. So we can say we are 95% confident. In other words, there's a 95% probability, that the true population percentage, in fact, I have it written out on this next page, lies between 14.1 and 19.9%. In other words, that somewhere between 95, we're 95% confident that the true population percentage that feel this way, getting bossed around is a bad thing about being a kid, is between those two. That's what we're saying. Okay. So we don't know if it's actually 17%, but we have 95% probability, 95% accuracy, if you will. The true population. Okay. All right, we're going to finish up here with other kinds of distributions. So this is what's called a right skewed distribution. This is what happens with incomes. I mentioned earlier in the section. You know, you have very few people making gobs and gobs and gobs of money, right, up here, the one percenters, if you will, and they drag, instead of being a normal distribution where the mean, median, and mode is all right here in the middle, all three of them, it drags that mean up away from the mode. So then the mean's up here, right? It drags the average up because when you average those out with these huge, huge numbers, these huge incomes up here, it pulls the mean up away from the mode, right? So the mode most often, uh, income would be there. Your median is up here, right? So it's skewed right. Whereas if you could also have a skewed left distribution where your mean is down here, your mode and your mode, sorry, and your median is right there. This would be like a lot of time faculty ratings, teaching ratings, or skewed left. Okay. So again, these are not normal distributions. These are other kinds of distributions, right? So this is a skewed right, tails off to the right. This is a skewed left, right? Tails off to the left. Okay. Thanks so much for watching. We will see you guys next time.